Hey guys, it's Rizzie here, currently at work, New York Sports Club childcare. So I thought I'd do a little experiment with you to pass the time. It's going to be really simple, and all you're going to need is a piece of paper. Although this experiment's so simple, it actually goes into a lot of theoretical physics, so you're going to have to stay with me on this. First thing you're going to want to do, take that paper, cut into a little strip. After you have your strip of paper, you're going to want to make a half of a twist in it, like this. And you've just created one of the biggest paradoxes of all time, the Mobius strip. Why exactly is this little guy so strange? Let's take a look. Taking a pen, start at one point of where you had taped it together. Starting at this point, make a line. Keep going straight down the paper, right down the middle. You might have to bend it a bit, but you just created one of the biggest paradoxes of all time, the Mobius strip. Keep going until the line reaches the end. What's this? You ended up where you started, but you wrote on both sides of the paper. How's that possible? See, even on a normal piece of paper, just linked together, when you draw your circle and your line on it, it only goes on one side of the line. See, it's not on the inside, just the outside. Some theories say that this little Mobius strip represents how time might behave in the dimensions above it. Time is the fourth dimension, according to most scientific theories, which means that, unlike the third dimension, which is cubes and solids like us, time is a line, because you know, it goes future, past, present. Let's treat the paper as if it were an infinitesimally flat, two-dimensional object. It has two sides, the front side and the back side. Since we can't observe time like that, we can see it on this little piece of paper. Let's treat the line we're going to draw with the pen as an infinitesimally straight line. Time might be represented as, in most situations, we draw. Making the straight line, this line will only travel on one side of the paper. It's going on a two-dimensional space. Since the line can't go anywhere except straight, it could never reach the back of the paper. But what if the paper was twisted the same way that the Mobius strip was? Let's do it. Let's try drawing the line again. Magically, almost, the one-dimensional line reaches both sides of the two-dimensional flat plane. Thinking of this in the same concept of time, however, would be saying that the line we have here represents time, and the two-dimensional fabric represents all the infinities of different outcomes that time could have. And by twisting this together, you pretty much make the timeline go to a completely different space. So this represents, actually, a form of time travel. I mean, it's obviously not time travel, it's a piece of paper, but you know, you get the point. We should, at least. Whatever, it's theoretical physics, don't worry. Hope you enjoyed this little bit of theoretical physics and I didn't fry your brain too much. If you want any more information, just click the links right here. If you liked this video, make sure to watch the others, or subscribe. Subscribe would be great. You know, I like science, you like science, we like science, Rizzie likes science. Science with Rizzie.